I hope you can gain something from this pencast. One of the biggest things that you can get from this is it's kind of all about where you're measuring from and making sure your measurements make sense in the context of how you're setting up the different aspects of your integral. So I'm going to try my best to make this as clear as I can. So here was the context. We got our yellow submarine. It was 8 feet. Well, the center of a window on the yellow submarine was 8 feet below the surface of the water. The water was up here. And because the window is vertical through the water, the pressure on it varies. Remember that pressure is that weight density, which of water, I'm going to say we're in fresh water, because if I said salt water, Devin would be mad at me. So I'm going to say we're in fresh water, and the weight of water is 62.4 pounds per cubic foot. That weight gets multiplied by the depth. They used H. I used H on my PowerPoint today. H is the depth in feet. And so when you multiply that weight, 62.4 pounds per cubic foot, times the depth in feet, you end up getting so many pounds per square foot, which is what pressure is. Now, if you take that pressure in pounds per square feet and multiply it by an area, the number of square feet that we're interested in, then you end up getting the overall fluid force or hydrostatic force. Now, that pressure again was pounds per square foot, and the area would of course be measured in square feet, and so you end up getting a force in pounds. Now, since the pressure is varying throughout my circular submarine window, because the height is varying throughout that, we do need to sum up and get integrals and figure out what slices look like and all that. So what I'm going to do here is I'm going to blow up that window, make it a little larger so we can see what's going on. The center of the window is here, has a radius of 1 foot, and let's just say for the sake of this problem, we're going to measure from the top down. And I'm going to call that, we'll call it capital D for depth. And let's say that we were going to think about a slice, say just right here. This is just a representative slice. I could have drawn it anywhere in the circle, but I got to draw it somewhere. We're going to make it calculus thin, so theoretically it's not really that gap there. It's following the circle really, really well, but just to see something, I got to draw this. So it's calculus thin, so that distance right there is just a little bit of D. If you could see my thumb and first finger pinching right now, you would see me talking about that DD, the change in depth, that little bit of depth. Now, the issue is this. I need to know the area of that strip. As you saw up here, we need to get the overall force, we need to take the pressure times the area of a strip, because within that strip, the pressure is always the same. So if I take that pressure right there times the area, I will get the force, and then if I sum up all the forces within that circular window, I'll get the overall fluid force. So I need to find the area of that, which means I need to know, I'm going to call that dimension x, and I'm going to cut that in half. I'm going to acknowledge that this is also an x over here, but I'm just going to focus on this right side, because if I drop this down, I know that that's also a radius of 1 foot. And so what I have here is x squared plus something squared on that other leg is equal to the radius, so the hypotenuse squared, which is the radius squared. The issue now is this leg over here. How big is it? Well, it's all going to depend on where I'm slicing, but as I get a representation here, here's what I would like to say. From the top of the water down. Now, if you went from the top of the water down to the center of the window, and then all the way down to the bottom, that would be a total of 9 feet. So, down here at the bottom, the depth is 9 feet. Now, if I back up something here, if I just back up the, however deep I actually am, we'll call it, I'm labeling that capital D for depth. So this distance here is the full 9 minus however deep I am at that particular stripe. Well, if this piece down here is 9 minus D, I know the whole radius here is 1, then the remaining piece here that I'm interested in is going to be 1 minus the 9 minus d, which corresponds to, if I distribute that minus sign, is negative 8 plus d, or probably looks better as just d minus 8. So this leg right here that I'm interested in is d minus 8. So I think that's what Cam had before, and I was just missing how he was measuring and how to think about it. So Cam, I apologize for messing that up this morning. Alright, so here we are. So the distance x that I desire then is going to be 1 minus that d minus 8 squared. So it's going to be the square root of 1 minus d minus 8 squared. Alright, let's take it from there then. So here's what I know. The pressure on that strip, let's just say, that slice in the window, is going to be the weight density of water. We're going to call it 62.4 pounds per cubic foot, times the depth, which is just going to be d. And now my depth is going to vary from, if you look back at my picture here, we were 8 feet deep right here at the center. So I could go up 1 foot to be at the top of the window, which would be a depth of 7 feet. Or I could go 1 foot below the center, which would be a d of 9 feet. So this window is living sort of between this depth of 7 feet to 9 feet. So keep that in mind, that this depth right here varies from 7 feet to 9 feet. Okay, now the fluid force is that pressure. Oh, and I should have labeled up here, d is measured in feet, and so I would get so many pounds per square foot, which is the definition of pressure. So take that pressure, 62.4 times d, and multiply it by the area of that strip. Now that little strip there is just a rectangular strip with, remember, x was just half the distance across, so I would need 2 of those x's to get the length across that rectangle, that distance being 1 minus d minus 8 squared, times that d. And if I sum up all of those forces between that depth of 7 and 9, I should get the overall fluid force. Just one more time, unit-wise, let's see if it makes sense. Pounds per cubic foot times feet times feet times feet, and then certainly feet times feet times feet over cubic feet, we're just going to get so many pounds. Now I did the old math 9. The way I typed this in my calculator is I did math 9, which brings up the FN int. I don't know why I put parentheses around that. Let me do that again. FN int. And then I typed in the 62.4 times 2, times x. On my calculator, I just pushed the x button rather than searching for the d button. Doesn't matter what variable you use. So 62.4 times x times 2 times the square root of 1 minus the quantity x minus 8 squared. That's it. Comma with respect to x, comma from 7, comma to 9. I think I got all that in right. 62.4 x, 2 times quantity, yeah, there it is. And when you put this in your calculator, what you end up getting is this. 1568 point about, we'll call it 3, pounds of force on that submarine window. Hope that helps. Send me an email if you have any questions, or stop by and see me between now and Friday.